Okay, the second video for 8.3, we meet the comparison test and the limit comparison test, and these are two of our most frequently used convergence tests for series in Calc 2. The comparison test is a little bit more primitive, but if it gets the job done, it's probably your preferred means of operating. The limit comparison test has a little bit more baggage to it, namely the limit, which often can provide a hurdle for some students or provide some trouble in some problems. But the limit comparison certainly has its place, and you'll need it in some cases where the comparison test won't work. So let's look at the theorem itself. Suppose there exists an m greater than 0 such that a sub n is between 0 and b sub n for some n greater than m. So in other words, we're thinking of some index. So somewhere along in the index of our sequence, 1, 2, 3, 4, maybe m is equal to 100. There's a point where any index past m, or 100 for instance, we can talk about, we know that this sequence, the sequence terms a sub n are less than the terms b sub n, so that this boundary is actually happening. So in other words, maybe we don't worry so much about where that index is, as long as eventually all of the a sub n are less than or equal to b sub n, or infinitely many of them are that way, then we can use this theorem. So if the series of b sub n terms converges, then the series of a sub n terms converges as well. Note that's forced by the fact that b sub n is larger than a sub n. So if we add up terms that are larger than one series and it's converging, in other words, it sums to a finite number, then if we add up the series terms for a sub n, which are necessarily smaller or at most equal to these convergent terms, then that series itself has to be convergent. So it should, more or less meet intuition. And similarly for the divergent case, if, on the other hand, a sub n, that series diverges, if we were able to know that or demonstrate that, then we would be able to conclude that the b sub n series diverges. And that's again because if a sub n is divergent, it's an infinite sum, or it sums to an infinite value, then we know that these b sub n, which are larger than a sub n, that series necessarily is going to have to be larger, or at least as large, so it's going to diverge as well. That also should meet intuition. Now, let's have a look at an example. There's sort of two main parts of this that I want to point out and be careful with. So we have a series n equals 1 to infinity, n squared minus 3 over n to the fourth plus 7. This is a pretty common type of problem. You'll see a lot of rational functions in the variable n for these series terms. The first thing that I like to write down, and I think a lot of students and people learning this will appreciate, is to kind of find the intuition for the problem. So you think of this almost like it is literally a rational function in a discrete variable n. We can think about it as a rational function in a continuous variable, and just consider what the degree of the numerator is versus the degree of the denominator. So in other words, n squared minus 3 has leading term n squared, n to the fourth plus 7 as leading term n to the fourth. So this series term as a whole is behaving, that's what the tilde is indicating, it's approximately equal to, or it behaves like n squared over n to the fourth. Then if we cancel the common powers, this is 1 over n squared. So this is our intuition. This is the way we look at it and say, you want to have a suspicion about this thing one way or another. You want to make a guess as to whether or not you believe it converges or diverges. But as soon as we see this 1 over n squared, we get a good feeling that it might converge. Because remember that 1 over n squared as a p series, that's p equals 2. 2 is greater than 1, so it's a convergent p series. Now, it seems like this thing should behave like 1 over n squared. So this is what gives us the comparison we want. Okay, so in this case, we have a series term. We think it probably converges because it seems to behave like this term. Now, the nice thing about that is we can say, well, let's use the given term to compare to the term we suspect it behaves like. If this given term is less than or equal to the one that we know the convergence of, the p series, then we can conclude that this series converges. So that's where we set up our comparison. And this is a nice equivalence of inequalities operation we can do here every time. If we suspect the comparison theorem is going to work for us, we'll just operate in this way every time. So we'll say, given series term, write it down as less than or equal to 1 over n squared, and make a declaration of, n is greater than 1. That's based on the fact that we're counting from n equals 1 up to positive infinity. So what we want to do here is this: we just want to use algebraic operations, legal on both sides, to get to a statement that we know to be true based on the characterization of n greater than or equal to 1. So in other words, if we work down these lines and we arrive at something that we know is obviously true, or see is obviously true for n values that are greater than or equal to 1, well, then we've got a valid comparison, so long as all of these steps we work through were actually valid or legal algebraic operations. One thing to be careful of, we do have a less than or equal to sign. If we multiply by a negative or flip fractions to reciprocals, then we want to be careful that we flip that an inequality sign. Otherwise, this is pretty straightforward. So it looks like we multiply both sides by denominators to arrive at the next line, actually carrying out the details of this one. And we're here. Distribute n squared across that binomial into the fourth minus 3 to the n squared. We're comparing left to right. Let's just combine like terms. So we'll add everything over to the right-hand side, and we end up with 3n squared plus 7 is greater than or equal to 0, reading from right to left, and n is great for n greater than or equal to 1. Well, this is obviously true really for any n whatsoever. But specifically, it's true for our n values of n greater than or equal to 1. So we've arrived at something that we can is plainly true, clear to see. This is a sufficient establishment of our comparison. So now we know that this must be true. This inequality holds. These were equivalent inequalities, and we arrived at one that is patently true. So the next step then is to tie it all together with the comparison test. So this is what's happening down in the language below. And this is something you should practice even when you're doing online problems where you're just declaring convergent or divergent. You should practice this language because this is a full correct answer on the exam, and you're expected to be able to do that. So we can state this as part of our answer, or summarizing what we had above. This series term is less than or equal to this function of n for n greater than or equal to 1. Since this series term, the greater one, is a convergent p series, then the comparison theorem implies that our given series, S, we named it S up here, actually converges as well, because it's the lesser series bounded by a convergent series from above. So this whole set of work from here down to the bottom, including the language at the base, is a full correct answer for full credit. So you need to make sure that you establish the comparison fully. If we were to stop here, you notice that it would be unclear whether or not this is actually true. It's kind of hard to see that. By the time you get here, there's no doubt as to whether or not this is actually true. We could even go further solving for n there, but this one's pretty easy to see. So when in doubt, show more details, of course. What I want to point out, though, this intuition side over here that we started with, this is not part of the answer. It's not necessary. It doesn't need to be in a test answer, but it's a helpful tool to use to get set up to establish the answer. The answer is actually more or less a rigorous mathematical proof. Without all the formal language at the beginning of it. So that's maybe the challenge of these problems, but that's also the expectation for them to be able to put an answer together that looks like this, not just declare convergent or divergent on a hunch. So let's see some more examples. So we've got a series 1 over 2 to the n factorial. We've named it S, and n goes from 1 to infinity. And first step, we're just going to write this as 1/2 to the n factorial. Now remember, n factorial, this is one of those cases where we have a discrete function, or a function for a discrete variable. Factorial is only defined for discrete positive integers. There is a way to extend it to real numbers. That's not for our course, but anyway, let's rewrite this term over here and think about what it might compare to. Well, the most obvious thing we can compare it to is 1 over 2 to the n. And that would be really handy because 1 over 2 to the n is the series term for a convergent geometric series. So what we don't have when we first write this down is that inequality, but a pretty quick check tells us n factorial, which is n times n minus 1 times n minus 2 all the way down to times 2 times 1. Recall that definition from a previous section. That number is larger than n. So in other words, 3 factorial is 6. Compare that to 3, which is smaller than 6. Again, that's in the exponent of this term. So that would make 2 to the n factorial greater than 2 to the n. So if we take the reciprocal, 1 over 2 to the n factorial is less than or equal to 1 over 2 to the n. Maybe I'll write that one detail off to the side here just to help clarify some things. But 2 to the n factorial is necessarily larger than n factorial. So 2 to the n factorial is greater than or equal to 2 to the n. So we've got that detail filled out. We're proving it a little bit further. This one's maybe a little bit more detail than we need, but nice work if you can do it. This is just provided to show that there's always generally a path in these problems to establish these inequalities exactly dead on. So this is just a matter of taking these logarithms, right? What we see here for each of these. So log base 2 eliminates that base in the exponent, and we just compare the exponents and arrive at that comparison, which is wholly believable for n greater than or equal to 1. So since this comparison holds and n equals 1 to infinity of 1 over 2 to the n is a convergent geometric series, the comparison test implies that S is a convergent series. So that was one that was not a rational function. Notice that that's an exponential function with a factorial in it. So things can get awfully weird, and they really will once we get into power series, just thanks to all the things that show up with representing transcendental functions as infinite series of polynomial terms. Now, second example is determine whether or not the given series converges. We've got n over square root of n cubed minus 2n. This is a rational expression. Remember, it's not a rational function because that radical does not keeps the denominator from being a polynomial. Again, though, we can go straight to intuition and say n is the lead term in the numerator, n cubed, but there's a 1/2 power outside of all of this. So n to the 3/2 is the dominant term in the denominator. And that's what we want to compare with. So notice really all we did here was say n cubed, there's a square root, so that's 3 over 2 in the exponent. So we have n over n to the 3/2. That's equal to 1 over n to the 1/2. And we know that as a p series to be divergent because p is less than 1. So that's our hunch. That's what we'll work with. And then we formulate our answer over here. So we declare a comparison that looks like this. We think if this thing behaves like 1 over n to the 1/2, it should diverge. If we can show that it's greater than or equal to 1 over n to the 1/2 for n greater than or equal to 1, well, then we've got the comparison we need, and we can declare divergence to the comparison theorem. So similar operations as before, just algebra around an inequality, and we arrive at 0 is greater than or equal to negative 2n for n greater than or equal to 1. That's true for all of those n values. All of our steps were legal to get us there. So we know that this comparison actually holds. And we've really done all the work for this by the comparison theorem or comparison test and the lines 1 and 2. In other words, this comparison. And I think we wrote over here for number 1 that, yeah, this is a divergent p series. We have that our given series diverges. So in other words, the comparison test and our given comparison here says that this series is divergent because its term is larger than 1 over n to the 1/2, which is a divergent p series. So we've seen some diverge, we've seen some converge, but the thing is the comparison has always worked, right? As soon as we wrote this down, we were able to arrive at something that was true. So the limit comparison is what saves the day when that doesn't happen. It's always worth your while to try the comparison test because it might shorten your work, but the limit comparison will help you through if the intuition is there, but you can't get the comparison. And that's what we have in the box above. So we have two series again, A sub n and B sub n. We don't need to compare them directly anymore, but we take the limit of their ratio as n goes to infinity. If that's equal to c, where c is some finite number that's greater than 0, then both series converge or both diverge. So what's interesting about this is if the limit of the ratio of these series terms is a finite positive constant, then these series convergences are married. If one converges, the other one must converge. If one diverges, the other one must diverge. They're bound together in that sense. So we'll use the same intuition, but this will help us get around a comparison that doesn't work. So the given series is, again, a rational function of n, polynomial over polynomial. So when we start this work over here, we write down, we say that n squared is the lead term in the numerator over n to the fourth in the denominator. N squared over n to the fourth is 1 over n squared. That's a convergent p-series. So our hunch is that this thing converges. It probably behaves like 1 over n squared. Now we go to the comparison. That's happening off to the left here. We've got n squared over n to the fourth minus 5n less than or equal to 1 over n squared, and n is greater than 1. So multiplying both sides by denominators or taking reciprocals, it looks like we multiply by the denominator on both sides actually to get what we've got in the line below. It's n to the fourth is less than or equal to n to the fourth minus 5n. Subtract n to the fourth from both sides. We've got negative 5n is greater than or equal to 0. For n values which are greater than or equal to 1, that doesn't fail in just one place. That fails for all of those n values. All you need it to fail for is one place. Typically, if it fails for one value and then holds true for many afterwards, then you could ignore the value it fails for. But at any rate, once we run past 1, n equals 1 or n equals 0 even, we fail in every case. So this is an easy one to see. We don't have the comparison that we need. So the comparison theorem doesn't help us here. Our intuition says that it converges, but that doesn't really establish anything mathematically. We've got to fill in the details of that and be rigorous for this. So this is where the limit comparison helps. So rather than try to force that comparison that we didn't get and we won't get, we take a sub n over b sub n, the ratio, and we'll take our given series term as a sub n and put that over b sub n. Note that we could invert that. It doesn't have to be our series term over our comparison term. It could be vice versa. As long as we converge to a finite positive number, we'll have the same result, that their convergences are tied together. So simplifying this complex fraction, we've got n to the fourth over n to the fourth minus 5n. Now we take the limit as n goes to infinity. Remember, that's what this is telling us to do up here in the theorem. And when we do that, n to the fourth matches n to the fourth minus 5n doesn't matter, but this this limit converges to 1. That's a positive finite constant. So the conditions of the theorem are met. So we can conclude that the convergence of this series is the same as the convergence of this series. Well, the second series is a known series. It's a p-series. It's convergent. So we can conclude by the limit comparison test that our given series S converges as well. And that's it for the limit comparison test. The difficult part of this is to probably negotiate the algebra on this limit and then to properly take this limit. So one more example. We've got, it looks like another rational function, polynomial over polynomial. So let's go straight to the intuition. N squared minus 5n over this n cubed function behaves approximately like 1 over n. N squared over n cubed cancels to 1 over n. So we're suspecting that this thing behaves like 1 over n, and we recall that 1 over n is a divergent p-series. P is exactly equal to 1. In fact, that's the harmonic series. We've seen now in 2 ways why that thing's divergent. So we suspect that our given series diverges as well. So let's see if we can bond this series convergence to the known harmonic series convergence. And here's the limit as n goes, all in one shot. The limit as n goes to infinity of our term divided by 1 over n. That's really just a matter of multiplying n by the numerator, right? When we flip and multiply through that division sign. And we've got the following below. n cubed minus 5n over n cubed plus the rest. And we see that as n goes to infinity, this thing goes to 1, which is finite and positive. And we can conclude that this series has the same convergence as this series through the limit comparison test. So in fact, this is kind of easier if you don't try the comparison test first. This is all you need for the limit comparison test. I won't typically constrain students on any test or assessment to use one or the other. If I were to do so, that would be a hint to keep you out of trouble or some kind of messy analysis that might bog you down. So the limit comparison test will always work when the comparison test will. The comparison test might work, it might be shorter, and it might be more intuitive. Both tests are very important. These things aren't going to go away. We're going to use them all the way through the end of chapter 8. So get lots of practice with this. And 8.4 will cover alternating series, which introduces negative terms into these series.